All right, so let's say we need to find the, we want to find the Bode plot for this particular circuit, a straight line approximation Bode plot. And we are given already the transfer function right here. So we might think that we're good to go, that we're set, but we'll notice that on the transfer function, we just are given j omega over omega c. We have the corner frequency, but for that quadratic term, but we don't know what that actually is. So to get that, we have to analyze our circuit here. And the first thing that we'll have to do, I'm whiting it out from where I wrote it earlier. The first thing that we have to do is to figure out what the values of our impedances are. And so let's say for our inductor, the inductor is going to be J omega L, and the capacitor is going to be minus J over omega C, and the resistor, of course, is just going to be R. Now, our transfer function is going to be, our transfer function is V out over Vn. And so if we look at our circuit right here, we can see that we can find voltage division by, and so our V out over Vn is going to be the same as Z of this part right here, the impedance of this part, over the impedance of the entire circuit. So this is going to be equal to the impedance of R in parallel with L over the total impedance. And so our transfer function, to get R in parallel with L, that's product over sum, so it'll be R times J omega L over R plus J omega L over, and our total impedance will be R J omega L over R plus J omega L plus the impedance of our capacitor. So that's plus negative J over omega C. Now we want to get this transfer function that we have to look like our transfer function that we were given, so that we can see what our corner frequency is.
It's starting to smell like sweet potato.
And so I see that I've got an omega c in the denominator, so I'll leave that, but I want to get rid of this r plus j omega L. So I can multiply everything by r plus j omega L over r plus j omega L. Now in the numerator, the r plus j omega L will cancel out. So, and I can do this, of course, because I'm just multiplying by 1. So when I multiply this numerator by r plus j omega L, that just cancels, and I get r j omega L. And in the denominator, the r plus j omega L times the first term, that cancels. So I get r j omega L. And then I get plus negative j times r plus j omega L over omega c. So now I'm still trying to make it look like this top function up here, and I see that I've got a j omega squared, so I'm going to multiply this by j omega over j omega and see what happens. So from that, I will get R L j omega squared over, now the j times the j is negative 1, that's its definition, so I get minus R L and then omega squared plus, and then the I don't want the omega to cancel in the denominator. Oh no, okay, so that's not omega c. That's I'm being silly. Okay, but so I need to have an omega squared. I need to have a j omega squared in the numerator. So let's get that. So I'll have minus j squared omega times r plus j omega L over omega C. Now let's see what that turns into. So we've got RL times j omega squared over minus RL omega squared. And then minus j squared is just 1. So because j squared is -1, so minus j squared is just 1. So this gets me r omega plus j omega squared L over omega C. Okay, so let's see how we're looking. Okay, I need a C in the numerator, and I need to not have that R. So I'm going to multiply by C over R over C over R. And let's see what that gets us. So in the numerator, the R will cancel, and I'll be left with the C. So I'll have LC j omega squared. And then in the denominator, the R will cancel, and I'll get LC omega squared plus, and then the C will cancel with the C in the denominator of the second part. And so I'll get R omega plus j omega squared L over R omega. Well, that's handy because now I have LC times j omega squared over LC omega squared plus, now I can break this up into 2 parts, R omega over R omega plus j omega squared L over R omega. Something's not right. Hold on. Nope, we're all good. Okay, so then we have LC j omega squared over, and then the R omega over R omega, that's just 1. And then if you look at the j omega squared L over R omega, that the omegas cancel, and I get that that is plus, or one of the omegas cancels, and I get that's plus j omega times L over R, and then plus LC omega squared. So that's almost looking like our transfer function. Our transfer function is given to be LC j omega squared over 1 plus j omega L over R plus, I think did I leave out a j here? Uh, oh, no. Is it supposed to be negative? Did I lose my negative? I lost my negative right here. That's negative. That's negative. It makes that negative. So, so what we're supposed to have, if we look at our transfer function, is we're supposed to have plus j omega over omega c squared. So I can write this as plus, and now j squared is negative 1. So j omega, that gets this and this. And then over 1 over the square root of LC squared, because that then equals this. Because if I square this, I get minus omega squared over 1 over LC, and that would bring the numerator up. So this tells us that omega c is equal to 1 over the square root of LC. Okay, so now we can plug our numbers in, and we had that L was 1, L is 1, C is 10 millifarads, so 1 Henry, C is 10 millifarads, R is 150 ohms, so 10 millifarads is 0.01 farads. Yeah, that was 1 Henry. So this then becomes, our transfer function becomes L is 1 times our capacitance, which is 0.01, j omega squared over 1 plus j omega times L over R, so 1 over 150 plus j omega over 1 over the square root of 0.01 times 1. So that's 1 over the square root of 0.01, which is 100. So this is 0.01 times j omega squared over 1 plus 1 over 150 j omega plus 100 j omega squared. And then to get this into the form that we need, well, what form do we need? Well, we really are almost there. We have it in the form we need because we know what the corner frequency is. The corner frequency is omega c, and omega c is 1 over the square root of 0.01, which is 100. So actually, I wrote this wrong. So this should be j omega squared over 100. Which is j omega over 10 squared. So our corner frequency is 10. Yeah, right. Okay, but the other thing that we might need to have is we might need to have zeta in case that we were asked for zeta. And so how do you find zeta? So this was a question that I was asked a lot before. So we know that this middle term right here, 1 over 150 j omega, has to equal j2 zeta omega over omega c. j2 zeta omega over omega c. j2 zeta omega over omega c. Oh, that's not a zeta, that's a c. And that has to equal 1 over 150 j omega. So to find out what c is, we set these two equal. We know omega cancels, j cancels, j cancels. We know what omega c is, it's 10. So 2c over 10 equals 1 over 150. And 2c times 150 equals 10, or c equals 10 over 300, or c equals whatever 1 over 30 is. Now, this problem, I don't know if the problem asked for it or not, but that's how you could find it if you needed to have it. And that's what's called the damping factor. Okay, so now that we have this, we would know that our constant is 0.01. Our constant term is 0.01. We have 2 zeros through the origin, or a 0 through the origin to second power, to second order, and a quadratic pole. So for the constant term, we get the magnitude is 20 times the log of k, so 20 log 0.01. So the log of 0.01 is -2, so this equals -40. And so we have a constant of -40. And then for the zeros through the origin, those have a slope of 20 and they go through 1. Oh, well, they would have a slope of 20 per 20n, and our n is 2. So what that means, so with n equal 2, so these give us a slope, so the zeros through the origin, that gives us a slope of 40, but it goes through 1. And then we have a quadratic pole, and the quadratic pole gives us a slope of -40, and it starts at the corner frequency, which was 10. And starts at 10. Okay, so now we can graph this. So our constant term was -20. Make that a little thicker. Constant term is -20. And then we had a 0 through the origin, so that goes through 1, and it was order 2, so it has a slope of 40, so that means it would be at the next decade, it'd be down 40 and up 40 over here. So let's draw that one. It's as good as I'm going to get. And then we had our quadratic pole. That's going to be 0 until it gets to 10. And then at 10, it'll have a slope of negative 40. So that means by the time we get to 100, we'll be down to 40. All right, so now if we want to add all these together, we see that here at point 1, we had a negative 20 and a negative 40, so we'd actually be all the way down at negative 60 right here. And then the slope is going to be a positive 40, so it will just follow along parallel to the kind of magenta line until we get to the point where we have the quadratic pole. So until we get to here. And then once we get to the quadratic pole, then we have a slope. The quadratic pole adds a slope of negative 40 to our previous slope of 40, and so that'll just cancel out, and we'll just have a straight line there. So there we have it.